Hey everybody, welcome to my next video. In this one we're gonna continue on the topic of USB peripheral. Last time we checked out how can we use the USB peripheral of our microcontroller to create a virtual COM port, a serial port, so you don't need to use an external USB to serial converter, which is very handy. So if you have your USB and you want to create some kind of keyboard or a custom controller, then today we're gonna talk about that just today. And we're going to talk about another class specification called the HID, or the Human Interface Device. This is a class specification from the USB and it manages keyboards, mice, game controllers, joysticks and stuff like that. So we're going to talk about how that works and how we can utilize it on our project. If you're new, every time I recommend the F4 Discovery board. It's the one that I'm using in all these tutorials, so you can follow along. You have the exact board, but you don't need to have. You just need to have a board that has an appropriate microcontroller that supports USB full speed peripheral and it has a USB connector for easy working. And that's it. Everything else is gonna be universally same. So let's start. I think the best part is to start with the specification of USB. So I have a couple of these PDFs over here that you can download on the USB site. And this one is the USB classification for HID, so the Human Interface Devices. And the first thing, oh, this is finicky. Well, the first thing is there are multiple classes in the human interface, like an audio class, let's say, is one type, HID is another, storage device and stuff like that. So previously we used the class as a virtual COM port, and today we're gonna use the HID class. And each class maybe has multiple protocols, and this one has keyboard and mouse protocols. So your peripheral can act either as a keyboard or a mouse, and maybe a joystick is a combination of those two as well. So everything else is like none or reserved. So this is what the device has to communicate to the computer, so the computer knows what it's dealing with. The next thing you need to know is, well, the USB specification is very high level, it's very complex. It's not like SPI or I2C, it's very complex. It's in the form of packets, and the packets are large and have a lot of different parts, but the part of the package we're concerned with HID devices is the report. And again, report is quite a big packet in and of itself. It has lots of information about the device, but the main part of this report is gonna be explained here. So report is combined with your data and a lot of preemptive and other reserved kind of parts, but the part of the report we're going to be talking about is the body that we're going to be sending. And on this page 70 of this PDF, it's common to use 8 bytes of this report. It's made of the first byte, which is the modifier key, and if we go to the modifier section, these are the Control, Alt and Shift, and the GUI, which is the Windows button, which is this one. So this is the modifier that's applied to any key press. And if we go back to other, the second byte is reserved, and the next 6 bytes are for your key, so they're called key bytes. And this one is the one they're gonna write when you press a key. The first is the first one, and the second is the second one, and the third. As you can know, if you press multiple keys at once, it just recognizes the last one. So if you write A here and B here, it's gonna just write B on the keyboard as standard. So you're just gonna use the third byte, or the byte number 2 in our case. So it's sending the data in this called reports. So these reports are going to be sent, and there are a few settings that we need to check out. The first is the report description, which is a kind of setting that gets sent by the USB device to the computer to tell the computer how to interpret its data. So the computer know what the letter A means and what the different combination of letter means. So we have to generate an appropriate report for our keyboard, in our case device. The next thing is also the USB settings for our HID settings for the computer, and this is the first settings the computer gets from the device, so it knows what type of device is, what driver to get, what is the power recommendation, what is the standard. Like in our case, we're gonna be using USB 1.0 full speed and stuff like that. So we're gonna have to check out those two things. Also in this large tutorial you can see all the implementation for the keyboard, so you can write this. In this case this is a 4-byte report, in our case it's going to be a 6-byte, so the 6-byte is the actual stuff that's being sent to the computer. And the next PDF, which is also on the USB side is the HID usage tables, and this is another important thing. It's like the ASCII table, which key gets pressed. I mean, in ASCII table, which number represents each symbol, a number, a capital, a lowercase letter, or a symbol, stuff like that. Well, we have one here as well, because it's not run by ASCII, it's by a separate USB standard. So if you go to the keyboard page, which is over here, these are all the different keys that can be pressed on your keyboard, defined by a decimal number and a hex number over here. So we have the keypad, the keyboard, different cancel, clear, here are the volume buttons, and of course we go to up, here are all of our letters. As you can see, each letter is small and a capital. That's because we need to use that before mentioned modifier, which modifies this key. So every time you press A or Shift A or Control A, it's always gonna send the number 4. With ASCII, there's a separate number for the lower and the uppercase. But including with this A, the modifier byte is gonna include the appropriate modifier, Control or Shift. So this is how we can do large numbers. So you have to cascade it, so A plus Shift and stuff like that. So these are the two important tables. So if you want to create text with your microcontroller, which we're not gonna do today, we're just gonna do basic, you should use this table, and there's probably some table generated online that you can import into your project and use it as a keyboard. So this is this of documents, we're gonna go back to them. Also, for that report that I mentioned, you have to create that report description, so your device, your computer knows what kind of signal it can expect. So in our case, we're going to use the typical 8 bytes long report. So this is one sentence that we're going to do. And the keyboard is going to be a type of report. So we can create this with the HID description tool that is provided by us to USB organization. You can download this, and it's a Windows application. But no problem, if you have Wine, you can also run Windows applications on your Linux. Also, this is the webpage /HID. This is all the data and documentation you need, and those two PDFs that I showed you before are these two over here, and this is all you're really gonna need. So if you go to the description tool, we can open, and it goes into the default directory, and it has a few presets, and we're gonna go for the keyboard preset. And if you open it up, you can see all the different settings for this report. What is the size, minimum, what it is, it's a keyboard and stuff like that. It's not really important. What you're gonna want to do is export it as an a.h file, as a library. In this case, it's gonna be very handy to us because it will generate report, so we can easily import it into our project. I already did that over here. So let's go, and I'm gonna open it in the Sublime, and I have this report open up right here. It should look something similar for you, and in this case it's a report long 63 long, so this is the data we're gonna need, and this is the guts of the report we're gonna need. So let's start. So I'm gonna go into the latest Cube IDE and start a new project. So you're gonna load up the project selector. In our case, it's the F4 Discovery board. I'm gonna leave it in the default workspace, and let's call it test F407 Discovery. And we're not gonna initialize. In this case, if you're not having the F4 Discovery or any other board, we're gonna go from the ground up, so it's same for everyone. So it's easier for you. As you can see, it already has the pins defined, but we're gonna reset that, so you can all start from the same page. So it's a blank processor. First, let's go for the clock. If you have a ceramic resonator, gonna enable this one, and let's go to the clock setting, and let's enable external one and clock it to, let's say, maximum, or what your processor supports. So you can see the external clock is selected. That's great. We're gonna also tick this one, so it's gonna generate those C and H files for the library in separate folders, so it's easier to manage, at least for me. And also we're gonna enable the serial wire debug. And now you need to enable the USB peripheral. Let's go to connectivity and the full speed. Some processors don't have high speed, so we're gonna use full speed as it's the most compatible because it's still USB 1.0 standard, so no drivers are needed. So this is the best one. So device only. And then the middleware, which is the software from ST that enables easier communication with the driver or the USB peripheral, so it's much easier for us to do stuff with it. So this is the middle device, and we have to tell it what class that we talked about before the USB device is. Previously you used the virtual COM port, but today we're going to use the human interface device. So you're going to select that, leave everything stock, because some of this data, especially PID and VID, is important for the drivers, but in our case it's probably gonna be cool because it's 1.0 USB. So these are all the settings that we really need, and so let's save it, and it's gonna probably ask you if you want to export it, and just click yes. And this is gonna generate our file structure. Let's close this and let's go to my preferred view. Okay, so let's go to our core where the main file is. So this is where we're gonna call all the code. And the middleware, this is a new folder, and if we go down this rabbit hole, here's the HID folder with the USB HID C and H files. We're gonna open those two because we're gonna use those. Also on the USB device, there's an app folder, and it has the USB device driver specifically. So this is what we're gonna use for the handle, because we have to address the peripheral somehow. So the first one, let's include the library for the USB HID. So it's just gonna copy this one and into here, so any future changes doesn't drive out our settings, so this is not gonna be affected if we change any settings in the IOC file. Next, let's just copy the handle, and because this handle is gonna be already defined by the USB device library and the HID library, we want to use it as externally defined. So let's go extern and copy that, so it's already defined handle, so it's not overwritten, so we're gonna use the appropriate one for this peripheral. Before starting any code, we need to set up our HID. If we go back to the HID.c, its default setting is for the mice, and as you can see it's a little bit ugly. Let's try compiling and see if it goes away. Yeah, this is the IDE stuff doing from time to time. And as you can see, if we go, this is the descriptor, so this is the first setting that gets sent to the computer. So this one is telling everything like power, the type of the device and stuff like that. And over here there's an interface protocol, so those are the ones that we saw before: mouse, none, and keyboard and reserved. So in this case we can see mouse is number 2, and that's what it's selected. So default, this whole project is for the mouse. So let's just change this to 1. And just change the full speed one. No need to change the others. If we go down, we can come to the, in this case, mouse report description. So this is the additional settings that get sent to the computer, so the computer know how to interpret data from our device. And this is for the mouse in this case. We're just gonna edit the innards and not rename the settings for keyboard, because if you're stuck or it doesn't work, so you can trace back to all the changes you've made, because I've done this before and it didn't work and I renamed a bunch of stuff. So let's just leave all the naming as it is and just change the guts underneath. So the report that you generated before, you just want to copy all the insights, and let's go back to our file and delete whatever is here. Let's go up and just overwrite it with our new data. Also, as we can see, it is addressed with the size, because this is an array and it's addressed with the size, and this size is also somewhere defined. If you control click, it's in the USB-D HID and it's by size 74, but in our case we know it's 63. So let's change this to 63U. Let's save it like that. And also, if it doesn't work anytime, remember this is in a library file, so if you do some changes in this test.ioc, these all changes will be run over. So you would need to create an external file with these new functions that get imported into this file, because this file will be overwritten if you make changes in the MX-Cube environment. So you'll need to change these settings the way they are now, like these settings, this on the beginning, and this in the library if you change it. So if you want to make this not happen, maybe I'll make another video how to create another file. But for prototyping by now, this is fine. So finally, let's go into our test and start using it. So first we need an array. So we need the that array that's gonna be injected into our report that's gonna be sent to the computer. So as we said, the standard that is also recognized by BIOS and everything is 8 bytes wide. So let's create an 8-bit array called, let's say, HID buffer, and it's size 8, and by default everything is 0, so all the values are 0, and that's because it also represents the 0 key state, so untouched. So this is the buffer we're gonna need, and let's start coding. Firstly, let's fill the buffer with appropriate data. In our case, let's utilize also the modifier key, so let's create a capital D. So capital D is actually D and shift modifier. So let's create that. We said that the modifier is the first byte. So HID buffer, the first byte is gonna be shift. And what is shift? Let's go back to our datasheet and we'll go to modifiers, and we can see that the modifier each modifier has its own bit in the whole byte. So each one of those bits, if it's set, then it means this modifier. So in our case, let's use left shift, which is the second bit. So second bit in binary is 2 in decimal. So let's just type in 2 in decimal. And the second byte is reserved, as we saw before. And the third byte is the one that we're gonna use. So HID buffer, the third is D. So what is D? Let's go back to our tables, and we can see that D is 7 in decimal. So let's type in 7. So this is gonna mean when it's sent to the computer that the D key is pressed and the shift key is pressed. So let's send it to the computer, and we're gonna use a code that I have on my second monitor. So this is the function that we want to use. It's the USB HID send report, and it's going to send report with the appropriate USB peripheral with the appropriate length. So the first is the pointer to our USB full speed handle. So this is this one. Then it's going to send report, which is our HID buffer. Yes. And the length of the buffer, and we know it's 8 bytes. So it's going to send that. Now we need a little bit of delay. The USB is a very fast standard. It can transfer lots of data very fast, but in stuff like intermediate stuff like USB and keyboard, it can be quite slow and it has a little bit of delay. So in our case, we're gonna need at least 10 millisecond spec timeout, but in our case, let's use 15 or 20 just to be safe. So we're gonna call HAL delay. Nope, not this one. Delay, and let's go, let's say 20. We're not in a rush. You can try 15 and 10, but if something not works, maybe you can try by, before doing anything else, increasing the delay. But this should be plenty. Next, we need to release the key, because if you just keep it down like this and have a very long delay over here, then the key is gonna be just continuously pressed and it's gonna be just flocking D all over our screen. So let's untype those or lift the keys up by writing 0 on all the bytes. So this is 0 and it's gonna get sent at 0. And now we could do another delay 20, but we don't want very fast typing on our keyboard because, well, it's typing on the screen and when you're trying to debug a program, it's quite annoying. So let's put like a 2-second delay. I found it very manageable, so you can click pause or anything like that. So this should work, and let's just compile it once more. We did everything. So now let's create the debug configuration. I already have mine for the Sega J-Link debugger that I have uploaded on my board, but if you have your STM32 fresh out of the box, you should use this one, and you should load ST-Link, and everything here should be default and it should work. So click debug. I'm just going to use this one and debug. So this is gonna compile again, upload the code and start the debugger over here. And I'm gonna connect the USB to my device. So my device is connected to the computer, and let's click F8, and this is gonna start the code. So as you can see, the capital letter D is printing every 2 seconds as expected. So this is pressing Shift D and releasing it and waiting 2 seconds. So it works exactly as it should. Another note, when testing all of this, I found a little problem that you might encounter when first running this code. For some reason it doesn't work. The computer might turn some error. So let's just stop this and let's go to our terminal. So it can do errors like this, device descriptor read errors or something like that, unable to enumerate USB device. It's like the settings of the USB aren't applied and not working for some reason. And I've searched it online, and the only possible solution is that the probably driver is not working correctly. Although it's very weird because this is the latest one. But what I've done is just go back to your configuration over here and don't change anything. Just, I don't know, and change something and change it back to as it was, so you can export it once more. And when you do that, when you save it again, then it resets all the settings that have been done. So these are all the settings we did here, like in this row and over here, and also this one. So you might have to repaste or reset those to R values again, and then it just kind of works like now. So your mileage will vary. Maybe it's a different library for different controllers, but I found this error with MindBoard as well a few times. So if any of you have it, please comment if you have a better solution than that. But in my case, it works after resetting it this time. But please remember that every time you do that, all the settings in these libraries do reset, because they do not have these user parts when you can insert your own code. So I'm looking for a little bit of update of that. So if I have a solution better, I'll post it in the next video or so. So this is the basic version of how you can do it. So you can do certain functions that can utilize these tables for these different letters and combine it to send numbers on your keyboard. And I saw a nice project where a man made a USB card with a microcontroller that upon boot up, it would become a keyboard that would type his LinkedIn profile on the browser and open the browser and stuff like that. So you can do lots of different kind of stuff. So this is the basic. I don't want to go into much more detail. If I'll make some neat functions for you, I'll provide it in the GitHub link below. So thank you for watching, and I'll see you next time. Hey guys, just one more thing. I added a bit of functions to the GitHub repository so you can start using it a little bit easier. So I added 2 functions. It's the USB keyboard send character and the USB keyboard send string. And I have my device on pause right now. Let's just look at the files real quick. It's all explanation on here in the C file. I have also the extern handle over here and the buffer over here defined, so you don't need to define it over here. So all you need to do in your main is include the USB-D HID library and my new library that should be included somewhere in the ints for the .h file and in the source file for the .c file. So if you go to the .h file, it just has the USB-D HID included, and in the .c file you can see that I have the send character, which is the main one, and then it's the send string. The send string is as usual, is just sending and calling the character function, and the character function is firstly checking if it's a character, a lowercase character. If it's not a lowercase, because this is in ASCII, if it's not lowercase, it's checking if it's a higher case, and in the both cases it's doing the same thing. It's creating a HID number character based on ASCII. So you're removing a from a character and adding 4, like in this case, or in this case we're converting a higher case to a lower case and then converting it to a HID character. And if it's neither of those, it has to be some kind of symbol, and I have just this much defined. You can add your own. Here is a space, dot, new line or enter, exclamation mark, question mark, and you can add anything, like you just copy one of these lines. Also, you can see that the exclamation mark is a combination of the shift modifier and a number 1 on the English keyboard. So you have to change this depending on your keyboard. It's all explained. So in the end, it's sending the appropriate report and then releasing the key. and that's it. It has the default 15 millisecond delay, and that's it. So these are the two functions I put for you together so you can start using it quickly. So go down to the description and go to the GitHub link to download these two libraries, and you can add it and start testing on your own. Cheers!